Okay, so hi everyone. Today we'll continue from where we left off last time. And so last time we defined symmetric tensors and symmetric tensor decomposition, as maybe you remember. So a tensor is symmetric if it has these symmetries in the entries, like a symmetric matrix is like this. This is a symmetric tensor of order 3. It has these entries all equal, and then symmetric tensor, a symmetric CP decomposition looks like this. Okay, so you just take a sum of R rank 1s, but they're symmetric rank 1s. Okay, so they look like this. And the symmetric CP rank is the smallest number R for which such a decomposition exists. And so I want to start today with just an example. So this would be the third example of an application, which is independent component analysis. Okay, so what is this? So here we have a random vector x, so x is a random vector. And let's say in Rn. And then we know that x equals to a times s, where a, let's say, is n by n, and s is also a random vector in Rn, but s has independent components. So s is s1 through sn, so these are independent variables. So these are random variables, S1 up through Sn. They're independent. And so our vector x that we can observe, so we can observe samples from x. Let's say we can observe this vector x. And we know that it's a linear transformation of S, which has independent components, and the problem is to recover A, so this mixing matrix. And one example that of this, so this is useful in many applications, but one example that I like is called a cocktail party problem, where you have, let's say, n people in different corners of a room talking at the same time, and there's n microphones, so the people would be S1 up through Sn, they're just saying some stuff, and then there's n microphones, these would be the entries of the vector x, so here maybe I can just write, so xi is going to be sum j from 1 to n, a, ij, sj, right? So each of the microphones records some, like a different linear combination of the speeches of different people. Now, I don't know exactly how the physics works, but apparently this is mathematically what happens. And so the question is, can you, from all of these n different microphones, recover the original, the speech of all the individual people, so you could separate the speech. So this would be really helpful if you wanted to hear what everybody's saying, or if you, for example, you wanted to clear away some noise or something like this. And so how can we solve this problem using tensors, tensor CP decomposition? So we can do this as follows. Okay, so first of all, let me give some remarks. So first of all, we would like to recover A. If we could recover A uniquely, this would be up to permutation and scaling of its columns. Because permuting the columns of A here would be the same as swapping some of the entries of S. So, and that we cannot know. I mean, that's just something that happens here. So Okay, and scaling the columns of A means also rescaling the entries of S. And that's also not something we can determine. So recovering A uniquely really means up to permutation and scaling its columns. Or if you want to think about the example, this would be, you know, a permutation would correspond to ordering the n people in some order. And we don't really care what the order is, or scaling their voices. Okay, so that's what we can try to do. And it turns out, so if if S has two or more Gaussian entries, recovering A uniquely. So this is what I mean by uniquely, up to permutation and scaling, is not possible. I don't know if people are familiar with the Gaussian distribution and so on, but maybe I can just give an example because I think this is a very interesting observation. So let's say we have two random variables, S1 and S2. They're both normal, let's say standard normal, 0, 1, or something like this. And they're independent. And what I'm trying to say is that now if I take this random vector S1, S2, you also know that that one is standard normal, with now mean the vector 0, 0. And covariance matrix 1, 0, 0, 1. So I don't know if you have seen this, the multivariate Gaussian distribution, but okay, we have this. And now, can you think about a linear transformation of this vector that is non-trivial, that is not a permutation, or scaling, that will keep the entries independent?
Any orthogonal transformation.
Exactly. So any orthogonal transformation. So if you pick U to be orthogonal 2x2 matrix, then U times S1, S2, I claim, is going to be again standard normal with mean 0. But then its covariance matrix. So when you do this, the covariance is multiplied on the left and on the right by U transpose. But this is again, 1, 0, 0, 1. And so I guess you could do orthogonal, and you can even here multiply by some scaling, diagonal scaling matrix. But the point is, okay, so now think about the original problem, right? So suppose we have two of the S's are standard normal, or just normal, they don't have to be standard, but they're independent. Then you can cook up some transformation using orthogonal matrices, and get another set of coordinates that are independent. So, this A you wouldn't be able to recover it uniquely. So this is the point, and I don't know if maybe you haven't thought about these things before. You can, as an exercise, prove it to yourself. And so there are actually stronger results than this. Okay, so there's the Darmois-Kirovich theorem. I think this is just pretty cool. So that's what, it's not related to tensors, but I think it's pretty cool. So let S1 approach N be independent, and variables, and let's take two linear combinations. So Y1 is some I alpha I Si, Y2 is some, let's say J, beta J, Sj. So I'm taking two different linear transformations. So if they're actually independent, so if Y1 is independent, Y2, then the variables sk for which alpha k and beta k are both not zero are Gaussian. So what this is saying is, now if you can find two linear combinations that are independent, then the only coordinates for which both the alpha and the beta are non-zero, they have to be Gaussian. Which seems like a very strong statement. Okay, so and if they're not Gaussian, then either alpha or beta has to be zero. All right, so some food for thought. And then it turns out, so then the result is, that kind of follows from this, but maybe it's not super obvious, is, so if at most one of the SI's is Gaussian, then the matrix A can be recovered uniquely, which means up to permutation and scaling of its columns. And one way to recover it is via tensor decomposition. So let me try to explain how to do this. Okay, so to do this, I have to define the cumulant tensor of a random vector. I don't know if people have already defined it, possibly not. So let me just do it here. So I'll just write the whole statement into a theorem. So let x be a S as before. S has independent components. And assume that the expectation of S is zero. So it's mean zero. We're going to center everything, and therefore also the expectation of X is zero. So let C4 to be the n by n by n by n. This is the fourth order cumulant tensor of X. So I'll define what this is. So i.e. the tensor with entries so C4, it's a four-way order 4 tensor, so it has 4 modes. So it's entry I1, I2, I3, I4, and I'm gonna say of X is what? So it's given by this. So I'm going to take the fourth moment, so this is called the fourth moment, where you just take the expectation of the product. I mean, okay, so if my variables were mean zero, here, this part, this would be more complicated, this formula, but because they're mean zero, my formula is much simpler. And now, what I'm going to do is I'm going to subtract the pairwise products. So xi1, xi2 times xi3, xi4 minus xi1, xi3, xi2, xi4. Okay, minus xi1, xi4, 2xi3. Okay, so that's the definition. And the statement of the theorem is that then this fourth order cumulant tensor actually has the following CP decomposition. So sum I from 1 to n on the I, and then AI tensor power 4, where A1, AN are the columns of A. Okay, so its decomposition contains precisely the columns of A, and of course, it's up to permutation, and there's this scaling lambda, which we also don't know. And in fact, it turns out that this scaling lambda is the fourth cumulant of S. So it's I entry of the fourth cumulant tensor of S. Okay, so so why are we using cumulants? Maybe is one question. Why didn't we use just moments? And I'll try to sort of answer this, and then maybe try to show you how to prove such a result. Okay, so let me first explain why we're using cumulants. So, why cumulants? And my first question is, what is the fourth order cumulant of S? What is the fourth? Can you say anything about this tensor? So this is also, S is a random vector, so this will be an n by n by n by n tensor, symmetric. But can you say anything more, given that you know S has independent entries?
Ask her. Is it like the sum of the cumulants of the entries of because cumulants are additive for independent variables, I think?
Oh, we'll talk about this actually. But maybe it's simple to just look at just one entry. So let's look at an entry I1, I2, I3, I4, where all of these I1, I2, I3, I4 are different. Because there's several cases, right? So let's say I1, I2. So if I1, I don't know, all different. They're all different. Okay, so if we look at the formula here, the expectation of, okay, maybe I'll just write this one down. So we're going to get the expectation of SI1, SI2, SI3, SI4 minus the pairwise product SI1, SI2 times SI3, SI4, and the other three. So what about this? Keep in mind that S has mean 0. And it's independent. Right, so the S's are independent, so this just factorizes, right? Like this, and this is already 0. And similarly, these will also be 0, 0, 0. So the whole thing is 0. Okay. Now, if you consider an entry where they're not all different, maybe some of them are repeated. So if there's one entry, let's say I1 is different from all of the other three, you can see that all of these products here, they will have E of SI1 in them separately, which is 0, so it will make everything 0. So the only way that this cumulant entry is non-zero is if they're either two equal ones, so I, J, J, or maybe all of them are equal. I. And so let's think about the I, J, J one. So here you would have Si squared, Sj squared, and in two of the, okay, I want it to be in one of them. Oh no, just in one of them, you're going to have Si squared, Sj squared, and the other two, you're basically going to have E of Si, Sj squared. But because there's 3 ways to burn them up, this is 2, but this will go to 0, and these 2 will cancel out, because Si and Sj are independent. So the point of cumulants, this is the main point of cumulants, is that because you're subtracting all of these pairwise products, you're canceling out these entries, so that the only non-zero entries are the diagonal entries. So this could be non-zero. It equals to E of Si to the fourth minus 3 times E of Si squared, and this is the kurtosis of Si, and if Si is Gaussian, this will be 0. So this will be 0 if Si is Gaussian. Any questions? Want to say something? So the point of the cumulants is precisely this. So you, so that if you have a vector of independent entries, this is diagonal. This is a diagonal tensor, meaning that the only non-zero entries are the I entries. The other ones are all 0. Okay, so this is 0. Any questions about this? Okay, and so, okay. And so what happens is that, so this is something that I'm not going to prove, but this is a sort of a lemma. And so there is a book called Handbook of Blind Source Separation, which is where this independent component analysis theory is talked about. By Comon and Michouten. So Comon is the same person from Comon's conjecture, which we'll discuss tomorrow. And there you can find all of this. And so I just put a lemma here that says, so we have x is equal to as, and it turns out then C4 of x, so this is not just for C4, it's for any cumulant of x, can be obtained from the fourth cumulant of S using something that I haven't defined, but I will briefly talk about it right now, which is called Tucker decomposition. So what you do, C4 of S, as I said, is a diagonal tensor, which can't quite draw here, but you can imagine it's a tensor whose only non-zeros are on the diagonal. And what you do is you take this tensor and you sort of multiply it by the matrix A along all 4 modes. So this, I will also define it formally in a second. And so how does it work? Okay, so this dot J, so given a tensor T, let's say of order of size n1 by nd, T, oh, and I want to have a matrix. So matrix A of size, let's say nj by m. T j a would be multiply t with a along the jth coordinate. Is defined, is a tensor, is of size n1 by nj minus 1 m. Plus 1 and d, and is given by tja, what is its entries, okay, and d is some, so it's just the same as matrix product, okay, so if t was just n1 by n2, I would just take t times a, and this would be n1 by m, but now t is much bigger, so it's really like matrix multiplication along one side. So, so sum k from 1 to and j of t I1 by k minus 1 k by k plus 1 id times a k j. Yeah, and that's it. So I just, you know, in matrix product, you just multiply over k. We have k here and k here. That goes from 1 to nj, and now we do the same, but we just multiply by n. And pictorially, this would be like I take my tensor and I multiply by a along 1. Let's say this is nj and this is nj. Okay, this maybe would be a transpose, I guess, in the picture, but I hope you see the point. And of course, with the definition of this multiplication, you don't need t to be diagonal or anything like this, but here, if we go back to our setting, this C4 of S is diagonal, and then the A's are just you multiply by A along all 4 sides. And it doesn't matter which order you do this multiplication, and in the end it's all the same. And so you get this really nice decomposition, which actually yields the CP decomposition. Where is it? Here, which says, and now you can see, you know, you have this diagonal here and the columns of A. So C4 of X is this CP decomposition that uses A. So this is one a very important application of CP decomposition, and basically decomposition of the moments in the cumulants is very commonly used in machine learning. Okay, so just to reiterate, we showed how that you can use decomposition of the data tensor or the probability distribution tensor or the higher order cumulant tensor.
Elina?
Yes.
I lost track of what the given would be here. Are you creating the cumulant tensor as a
Oh yes,
tensor?
okay, good question, yeah. So what you're given is samples from X, and so you could create an empirical version of this cumulant, so it won't be exact. So you will get this tensor, yeah. So if you have samples, you can create all of these sample moments, which will give you sample cumulants.
So you
Yeah,
really
so-
do create a full 4 tensor.
Yes, and then you can decompose it to find A. Okay. Any more questions? All right, so now I would like to move on. Oh, there's a question?
No, it was just carrying on from what you had said, trying to parse what that implied. Thanks.
Sorry, quick question.
Mm-hmm.
Wait, so you're given the X, trying to find S and A, and it's that rank decomposition that gives you the A, and then the structure is that you're just able to do this like sides. I forgot what the terminology for the dot sub J is.
Yeah, this is Tucker product. I didn't say it. This is Tucker product. Okay, so this is called Tucker product. And it deserves way more than 1 minute.
But the A comes from finding the rank decomposition of the
Yes, exactly.
The
So
C4.
Exactly. So here I tried to sort of prove to you why you get this why C4 of X decomposes like this. And yes, so you would observe this C4 of X, and then you would compute this decomposition and find A, and you would also find the 4 cumulant of S. But that's really all this would give you. Yeah, the point is that if you have A, then maybe you can sort of decouple your samples. Like now, you can just, if A is invertible, you can multiply X by A inverse and then get samples from S, for example. But does this answer your question?
Yes, thank you.
Okay.
Can I ask, why do we use the 4th cumulant? If I'm not mistaken, we could play this game for any cumulant, couldn't we?
Yeah, that's a great question. So you could also use the third cumulant, which actually is the same as the third moment if you assume that if you assume the mean is all 0. And So one issue with the third moment is that if your distribution is symmetric, so like around 0, like this, okay, I can't do it, but for symmetric distributions around 0, the odd order moments will vanish. That's a bit of an issue, and yeah, it is not as precise because the fourth cumulant is sort of more, it's like positive in a way. Things could cancel out for the third
So the
one.
fourth is like the first one where everything is nice and we could go higher, but that's just doing more work for no reason.
Yeah, exactly. You could go higher. Yeah, and so the third cumulant might be 0 where you don't want it to be 0, and the fourth one, yeah, is like this, and the fifth one could also be 0. And the higher you go, the more error there is in the estimation of this empirical cumulant, so you really want it to be lower. All right. More questions? Okay, so I would like to talk about algorithms for sequence transposition, and there are many algorithms that exist, and I'll just mention 2 more in depth and maybe touch upon a third one, but because tomorrow I want to talk about the theoretical aspects of CP decomposition, we'll see. So we'll see how it goes. But one of the most well-known algorithms, the most well-known algorithm is called alternating least squares, which I'll talk about later today, hopefully. But first I wanted to talk about Jenrich's algorithm. And this one is actually for decomposing low-rank tensors. So it wouldn't work for any tensor. It would work for a low-rank tensor, which I'll define in a second. But it is actually an efficient algorithm that you can prove converges with a probability 1 to the correct decomposition. So let T be tensor of order, so now we're going to be real. So AI, tensor BI, tensor CI. So it has order 3 and is N1 by N2 by N3. And suppose that it satisfies the following 3 conditions. So first, you want these vectors AI, they lie in Rn1, are linearly independent. Then the vectors, the vectors Vi are linearly independent. And finally, every pair of vectors in CI is linearly independent. So of course, you can also assume all of the CIs are linearly independent, but it's a slightly weaker condition is enough. And one thing that we can say already from here is that since you want to have R linearly independent vectors in an Rn1 and an Rn2, this would imply that R, which is also the rank, or if a bound on the rank, is at most the minimum of N1 and N2, right? Because you cannot have more than N1 linearly independent vectors in Rn1. Okay, and so this is what we mean by low rank. And I'll talk about this tomorrow. Because for a matrix, this would be the rank, right? So if you have an N1 by N2 matrix, then its rank is at most the minimum of N1 and N2. But for a tensor, it turns out that the rank can be much higher. So I guess yesterday when we tried to think about it, it seemed like the rank could be n1 times n2. And indeed, that is the sort of the maximal rank. But we'll hopefully have time for this tomorrow. But so this Yenrix algorithm is a way to decompose such a tensor. And it comes with a theorem, so it says let T be of this form. And if it satisfies, I don't know, I feel like I already did this, but okay. Let T satisfy 1, 2, and 3. Then there exists an efficient algorithm to find the decomposition. The decomposition with probability 1. And you'll see where this comes from. Okay, and so how does it go? So what we're going to do is we're going to see how this works. So let's take our tensor T. And let's pick two vectors, u and v, in Rn3, random. Okay, and now what we're going to do is we're going to take the Tucker product, luckily we briefly defined it, of T with u along its third mode. So basically, it's like matrix vector multiply, n times u, but now it's T times u, and you have to choose along which side, because there's 3 sides. And so what does that look like? Well, so T is n1 by n2 by n3. So if you're multiplying with a vector of size n3, you're going to get a matrix of size n1, n2, n1 by n2. So it looks like this: sum j from 1 to n3, uj times t, maybe I should switch them. So t dot j, which means the j slice of t times uj. So this here is the j slice. So it's of size n1 by n2. Okay, so it just looks like this. If this was a matrix, you would just take mij times uj, but of course now we have slicing. Okay, and another notation actually for this. Sometimes we say t dot u. So here you could also put vectors. You put a, b, u, which would mean multiply t by this on the first mode, this on the second mode, and this on the third mode. But since we're not multiplying this first and the second mode, we just leave a dot, and then we put a u along the third mode. So these are different ways that people write this. And just to make things even more complicated, we denote this by tu. I don't know why, but this is our notation, just for short. And okay, so let's just expand and see what this actually equals. So we have sum j from 1 to n3. Here we have sum I from 1 to r. So what is the j slice, right? So we have AI tensor bi, and the j slice would be dij. Just take the jth entry of this vector, and then you multiply by uj. So I'm just sort of plugging in the expression for t into here, and taking the j slice, and okay, that equals to sum. I'm going to swap the sums, so I have sum I from 1 to r of And now here, I have AI tensor BI, but I also have this other sum over j from 1 to n3 of Cij times Uj. And this is just the dot product of these two vectors, Ci and U. Like this. Okay, so I have sum from 1 to r, Ci U times AI tensor BI. And if you now want to expand this sort of in a matrix way, we have matrix A1, A, R. Now here I have this matrix C1.U. These are diagonal entries, C, R, U. And then finally I have the B's, so V1 transpose, VR transpose. Okay, so I have, so if I multiply by a random vector U along the third mode, what I get is a matrix which has this kind of decomposition. Okay, so this here, this is the diagonal matrix here with zeros here. And I could call this A, so this is my matrix A. I'm going to call this matrix DU. So this is the diagonal matrix whose diagonal is exactly C1.U up through C1.U, and then V transpose. And similarly, if I do the same thing but with the different vector V, so T, I multiply with another vector V, which is also random, I'm going to get the exact same thing but with A, D, V, E transpose. Okay, so now V, everything here in DV will be given by C I dot V. So this is V. All right. So this is what I can get. And now, how does this work? So suppose for the next couple minutes that we can take inverses of any of these matrices, even though they're not square. Okay, so suppose we can take inverses. So what happens is, if I do, oh, and I'm going to call this TD. So this, remember, was TU, and this is TV. So if I take TU times TV inverse, well, I have A, DU, B, and then A, D, B inverse, and now I'm going to just pretend that I can take inverses, and afterwards we can switch it to pseudo inverses. But let's just pretend we can take inverses. B and then B inverse, D, V inverse, A inverse. So here the B's are going to cancel, and I'm going to get A times DU, DV inverse, A inverse. And what is this DU, DV inverse? It's actually, I mean, they're both diagonal, right? So this will be C1.U divided by C1.V, first entry, 1 entry, and then C1.U divided by C2.U, C2.V, up through CD.U, CD.V. So this is what happens if I take these two diagonal matrices and take the inverse of one. I just multiply with the reciprocals here. So assuming that C I U C I V is different for, oh sorry, inverse, from CJU CJV, then this is an eigendecomposition, right? So this is an eigendecomposition of TU V inverse. And assuming that my eigenvalues are distinct, we can recover the eigenvectors A1 up through AR, which are the columns of A, and eigenvalues, oh sorry, I should have R, right? And the eigenvalues. C on U, U on V, C R U, C R V. Okay, so this is, maybe we have cheated a little bit because we assumed everything was invertible, but, okay, so please bear with me. And similarly, we can do the other way. So if we take TU inverse times TV and the whole thing transpose, now you can try to verify this. And if you can take inverses, then you will get V times DU inverse DV, V inverse. And again, this matrix now, which is the matrix of eigenvalues, is exactly the inverse of this matrix. So, because they're diagonal, so it's exactly the one with C1V divided by C1U up through CRV divided by CRU. And so we can recover the P1s, the eigenvectors, P1 through dr and eigenvalues, just from doing eigendecomposition, so which are the reciprocal C1 of the and then assuming that, making this assumption that these are distinct eigenvalues,